Right now, something extraordinary is happening in our solar system. An object older than Earth itself has traveled billions of years across the galaxy to reach us, carrying secrets from a time when our sun didn't even exist. This isn't science fiction. This is 3IATLAS, and its arrival has quietly transformed our understanding of what moves through the cosmic darkness between stars. Professional disclaimer. This video examines published scientific research and astronomical observations for educational purposes. All interpretations and speculative discussions are attributed to their respective sources and the broader scientific community. For most of human history, we believed our solar system existed in relative isolation, a quiet neighborhood on the outskirts of galactic activity. The occasional comet would sweep through from our own distant Oort cloud, and asteroids would follow their predictable paths between Mars and Jupiter. But in recent years, that peaceful picture has been shattered by visitors from impossible distances, objects that have journeyed between the stars themselves. The first was Oumuamua in 2017, that mysterious cigar-shaped object that puzzled astronomers with its strange acceleration and complete lack of visible outgassing. Then came I/Borisov in 2019, which behaved more like a traditional comet, but still carried the unmistakable signature of interstellar origin. And now we have 3IATLAS, discovered on July 1st, 2025, by the ATLAS Survey Telescope in Chile. What makes this third interstellar visitor particularly fascinating isn't just its ancient origins or unprecedented size. It's the way this cosmic wanderer is revealing secrets about galactic evolution that we never expected to uncover. Some researchers suggest that 3IATLAS could be between 7 and 14 billion years old, making it potentially older than our entire solar system by more than 3 billion years. When the James Webb Space Telescope turned its infrared vision toward 3IATLAS in August 2025, astronomers discovered something that challenged fundamental assumptions about comet formation. The observations revealed a chemical composition unlike anything seen before in our cosmic neighborhood. Dr. Martin Cordner, leading the Webb observations, noted that 3IATLAS contains the highest ratio of carbon dioxide to water ever measured in any comet. This isn't just unusual, it's scientifically provocative. In typical comets from our solar system, water ice dominates the volatile inventory. But 3IATLAS appears to be enveloped in vast quantities of carbon dioxide, suggesting formation conditions dramatically different from those that created objects in our local stellar environment. The implications of this chemistry are profound. Carbon dioxide condenses from protoplanetary disks only in the frigid outer regions, far beyond where water ice typically forms around young stars. For 3I/ATLAS to contain such extreme ratios suggests it either formed in the distant reaches of a much larger planetary system than our own, or around a star with fundamentally different characteristics than our Sun. But the chemical mysteries don't end there. Observations from Chile's Very Large Telescope revealed another puzzling signature: prominent emissions of nickel vapor without corresponding iron signatures. In our solar system, these metals typically appear together in roughly equal proportions, reflecting the standard stellar composition. The apparent absence of iron relative to nickel in 3IATLAS hints at processing or formation conditions that remain scientifically enigmatic. These aren't merely academic curiosities. Each unusual chemical signature provides direct sampling of processes that occurred billions of years ago in regions of our galaxy we may never visit with spacecraft. 3IATLAS essentially functions as a time capsule, carrying authentic samples from stellar environments that existed during the Milky Way's youth, when star formation rates were higher and the distribution of heavy elements was dramatically different from today's configuration. To understand what 3IATLAS represents, we need to contemplate a journey that spans both unimaginable distances and geological timescales. Current modeling suggests this object originated from the Milky Way's thick disk, a population of ancient stars that orbit above and below the thin plane where our Sun resides. The thick disk contains some of our galaxy's oldest stellar populations, formed during an era when the Milky Way itself was younger and more chaotic. If 3IATLAS truly belongs to this ancient stellar community, its formation occurred during cosmic conditions vastly different from those that created our solar system's familiar objects. Matthew Hopkins, from the University of Oxford, presenting research at the Royal Astronomical Society's National Astronomy meeting, estimates with 68% confidence that 3IATLAS formed between 7.6 and 14 billion years ago. This temporal range places its origins in an epoch when our current solar system didn't exist, when the chemical composition of interstellar space contained different proportions of elements forged in earlier generations of stars. The object's ejection from its parent system likely occurred through gravitational interactions with giant planets or close stellar encounters. Once flung into the interstellar medium, 3IATLAS began a solitary odyssey through the near vacuum between stars, preserved in cosmic deep freeze at temperatures just degrees above absolute zero. During its billions of years of wandering, the object experienced occasional close encounters with other stellar systems. Recent modeling by researchers has identified at least 25 stars that 3IATLAS passed within 3.3 light-years of during just the past 10 million years. Each encounter would have slightly altered its trajectory through subtle gravitational perturbations, gradually reshaping its path toward our solar system. What's remarkable about 3IATLAS isn't just its ancient age, but the fact that it survived its billion-year journey through interstellar space while maintaining structural integrity. The environment between stars, while extremely sparse, isn't completely empty. Cosmic ray bombardment, interstellar dust impacts, and thermal cycling would have gradually modified the object's surface composition and internal structure. High-energy particles from distant supernova and other galactic phenomena would have broken chemical bonds through radiolysis, created exotic isotopic ratios, and possibly generated entirely new molecular species not found in typical solar system materials. The extremely cold temperatures of interstellar space, typically around 3 Kelvin, would have preserved most volatile materials in solid form throughout the journey. Yet 3I/ATLAS arrives in our solar system displaying vigorous cometary activity as solar heating drives sublimation of its ancient ices. Current measurements indicate the object is releasing approximately 129 kilograms of carbon dioxide per second, along with smaller quantities of water vapor, carbon monoxide, and other volatile compounds. This outgassing rate demonstrates that billions of years of interstellar processing haven't eliminated the comet's ability to respond dramatically to stellar heating. The object's nucleus, estimated to span between 440 meters and 5.6 kilometers in diameter, contains enough volatile material to sustain this activity level for months as it approaches and recedes from the Sun. Some researchers, including Harvard's Avi Loeb, suggest the comet may be significantly more massive than initial estimates indicated, potentially weighing over 33 billion tons and spanning 3.1 miles in diameter. The discovery of 3IATLAS has fundamentally altered our perception of our solar system's place in the galactic environment. Rather than existing in cosmic isolation, we now recognize that our stellar neighborhood functions as a busy intersection where ancient travelers from distant worlds regularly pass through, carrying information about their origins across vast expanses of space and time. Current statistical models suggest that objects like 3IATLAS should be relatively rare, perhaps one detectable interstellar visitor every few years under optimal observing conditions. But if these estimates prove conservative, enhanced survey capabilities from facilities like the Vera Rubin Observatory could reveal that dozens or hundreds of such objects pass through our solar system annually, most remaining undetected due to their small size or low activity levels. This revelation transforms interstellar archaeology from speculative science based on individual exotic objects into a systematic survey discipline capable of characterizing chemical and physical properties of planetary formation across different galactic environments. We could begin mapping the distribution of stellar metallicities, volatile inventories, and planetary architectures by studying debris streams that carry samples from distant worlds directly to our telescopes. The implications extend beyond academic astronomy. If interstellar space contains abundant organic compounds and volatile materials that originated in diverse planetary environments, then the chemical ingredients essential for biological processes might be distributed far more widely throughout the galaxy than current models suggest. But studying these cosmic messengers requires continued investment in the detection, tracking, and characterization capabilities that made the discovery of 3 IATLAS possible. The same technologies that allow us to identify interstellar visitors also provide crucial infrastructure for monitoring potentially hazardous asteroids and understanding our local cosmic environment. The scientific response to 3 IATLAS represents one of the most comprehensive observational campaigns ever mounted to study an interstellar object. NASA assets participating in the coordinated effort include the Hubble Space Telescope, James Webb Space Telescope, the Transiting Exoplanet Survey satellite, and numerous planetary missions throughout the solar system. The European Space Agency has redirected multiple interplanetary spacecraft, including Mars Express, the ExoMars Trace Gas Orbiter, and the Jupiter Icy Moons Explorer, to observe the comet from various vantage points across the solar system. This multi-platform approach provides unprecedented geometric coverage and spectroscopic resolution for characterizing an authentic sample from another stellar system. Hubble's continuing observations have captured striking images of 3 IATLAS, revealing a distinctive teardrop-shaped coma extending at least 35,000 miles behind the nucleus. The visual documentation shows classic cometary features enhanced by the object's unique composition and ancient origin. Because Hubble tracks the fast-moving comet across the sky, background stars appear as streaked trails in the exposures, creating both artistic and scientifically valuable records of this interstellar encounter. Ground-based observatories worldwide have contributed crucial spectroscopic data throughout the comet's approach. The Very Large Telescope in Chile has monitored the steady increase in nickel and cyanide emissions as 3 IATLAS responds to increasing solar heating. These observations provide quantitative measurements of outgassing rates and chemical evolution that illuminate the object's internal composition and volatile inventory. Amateur astronomers have also played essential roles in the observational campaign, providing continuous monitoring that professional observatories focused on multiple targets cannot maintain. While 3 IATLAS remains too faint for casual observation, experienced astrophotographers using sophisticated equipment have documented changes in tail structure and brightness variations that complement professional observations. The coordinated international effort demonstrates the extraordinary scientific value of studying this ancient visitor, while highlighting the collaborative nature of modern astronomical research. The protocols developed for observing 3 IATLAS will prove directly applicable to future interstellar visitors and potentially hazardous asteroids requiring rapid characterization. As we continue to unravel the secrets carried by this cosmic time capsule, one question becomes increasingly compelling. What else is moving through the darkness between stars, carrying messages from stellar systems we may never reach? The answer may reshape our understanding of how worlds form around other stars and what it truly means to be cosmic citizens in a galaxy where 400 billion stars constantly exchange their most precious materials across the vast distances of interstellar space. But here's where our story takes an intriguing turn. As 3 IATLAS continues its ancient trajectory toward the Sun, we're approaching a critical moment in astronomical history. The comet is entering what researchers call the observation shadow, a period when our most powerful telescopes will lose sight of this cosmic messenger just as it reaches peak activity. The timing presents both extraordinary opportunity and profound frustration for the global scientific community. As 3 I/ATLAS approaches perihelion on October 30th, 2025, solar heating will drive the most vigorous outgassing of its billion-year journey. Ancient volatiles locked in solid form since the object's formation will transition to vapor phase, potentially revealing subsurface materials that have remained hidden throughout its interstellar odyssey. Yet this crucial encounter will unfold behind the overwhelming glare of our nearest star. From Earth's perspective, the comet will pass within 10 degrees of the solar disk, buried in twilight conditions that render precision astronomy impossible. The same stellar radiation that promises to unlock the deepest secrets of this interstellar visitor will simultaneously hide it from human observation. Dr. Michelle Bannister, leading the trajectory analysis, describes the situation with characteristic scientific understatement. The period around perihelion represents the most scientifically valuable phase of the entire encounter, when maximum thermal processing might expose chemical signatures from the comet's primordial formation. But observational geometry places these revelations beyond the reach of our most sophisticated instruments. The enforced hiatus creates tantalizing questions about structural survival. Will 3 IATLAS emerge from perihelion as a single coherent object, its ancient architecture intact after surviving both billion-year interstellar journey and intense solar heating? Or will thermal stresses finally overcome whatever forces have held this cosmic wanderer together, fragmenting it into multiple pieces that create expanding debris clouds visible as separate cometary objects? Historical precedent offers limited guidance. Most solar system comets that fragment during close solar approaches are fresh visitors from the Oort cloud, encountering significant stellar radiation for the first time after millions of years in cold storage. 3 I/ATLAS represents something fundamentally different. A battle-tested survivor that has already demonstrated remarkable structural stability during its epic voyage through the interstellar medium. Earth's orbital motion around the Sun gradually improves viewing geometry for objects that pass close to our star, and patience will be rewarded. By early December 2025, 3 IATLAS will begin emerging from solar glare into prime observing position, offering telescopes worldwide their best opportunity to study intact interstellar material. The comet's calculated closest approach to Earth occurs on December 19th at approximately 1.8 astronomical units, roughly 270 million kilometers distant. While this might seem vast by terrestrial standards, it represents optimal conditions for detailed spectroscopic analysis. The distance places the object close enough for major telescopes to collect substantial photons, far enough to avoid atmospheric interference from Earth's thermal radiation, and positioned in pre-dawn skies where background contamination reaches minimum levels. Some researchers suggest this December observation window may represent the finest opportunity to characterize authentic extraterrestrial material that human science might encounter for decades or centuries to come. Unlike previous interstellar visitors that departed quickly before comprehensive study could be completed, 3 IATLAS follows a trajectory and timeline that keeps it within range of major observatories well into 2026. The extended observability stems from the object's moderate approach velocity and favorable geometric circumstances, Where earlier visitors like Oumuamua swept through the inner solar system too rapidly for detailed investigation, this ancient wanderer offers months of sustained observation across multiple wavelength ranges and observational platforms. Professional observatories have already begun preparing coordinated campaigns designed to extract maximum scientific value from the December re-emergence. Spectroscopic programs will monitor chemical evolution as the comet responds to changing solar heating conditions. Photometric observations will track brightness variations that might reveal internal structural properties or rotational characteristics. High-resolution imaging will document morphological changes in the expanding coma and tail structures. The stakes extend beyond academic curiosity. Chemical signatures preserved in 3IATLAS could provide our first detailed glimpse of planetary formation processes, operating under conditions dramatically different from those that created our local solar system. Every spectroscopic observation represents direct sampling of stellar environments that existed billions of years ago, when our current cosmic neighborhood remained unformed. What makes the December observations particularly significant isn't just the opportunity to study this individual object, but what 3IATLAS represents for our understanding of galactic-scale material exchange processes. Current statistical models suggest interstellar visitors should arrive infrequently, perhaps one detectable object every few years under optimal survey conditions. Yet some researchers now question whether these estimates might be conservative by orders of magnitude. Enhanced detection capabilities from next-generation survey systems could reveal that our solar system receives far more interstellar traffic than previously recognized. The Vera Rubin Observatory, which achieved first light in 2025, will eventually rescan the entire accessible sky every few nights with unprecedented sensitivity. If such surveys demonstrate that dozens or hundreds of interstellar objects pass through our cosmic neighborhood annually, the implications would fundamentally transform our perception of planetary system evolution and galactic chemical processes. Rather than viewing Earth and its companions as isolated products of local stellar formation, we would recognize ourselves as participants in galaxy-wide ecosystems, where material constantly flows between stellar systems across vast distances and timescales. This perspective shift carries profound implications beyond astronomical research. The infrastructure required for monitoring interstellar visitors and studying their chemical compositions provides templates for addressing global challenges that transcend terrestrial boundaries. Precision detection systems, rapid response capabilities, and international coordination mechanisms developed for cosmic archaeology could prove equally valuable for climate monitoring, pandemic response, or resource management. More fundamentally, awareness of objects like 3IATLAS offers perspective on humanity's place within galactic-scale processes operating across geological time. The carbon atoms comprising our bodies were forged in stellar furnaces that expired before our sun ignited. The water we consume may have arrived via comets from distant reaches of the early solar nebula. The atmosphere we breathe contains elements that traveled between stars for longer than complex life has existed on Earth. Recognition of these connections transforms environmental stewardship and international cooperation from abstract moral imperatives into practical necessities for cosmic citizenship. We cannot afford to squander the rare conditions that allow complex chemistry and biological evolution to flourish on planetary surfaces. Nor can we fragment our capabilities through short-sighted competition when addressing challenges operating on galactic scales. As we prepare for 3IATLAS to re-emerge from behind our star's overwhelming brilliance, carrying chemical signatures from stellar environments that predate our solar system by billions of years, we stand at a remarkable threshold in human understanding. This ancient wanderer represents more than scientific curiosity or astronomical achievement. 3IATLAS functions as a messenger from deep time, carrying direct physical samples from processes that shaped our galaxy during its youth when star formation rates exceeded current levels and heavy element distributions differed dramatically from today's configuration. Every molecular emission line detected in its expanding coma provides authentic data about conditions that existed before Earth began forming from the solar nebula. The object's unprecedented chemical composition, its apparent great age, and its successful navigation across interstellar distances demonstrate that our cosmic environment contains far greater complexity and connectivity than our Earth-centered perspective typically allows us to appreciate. What appears extraordinary from our limited viewpoint may represent routine business on galactic scales, where 400 billion stars continuously exchange materials across the vast expanses between stellar systems. Yet studying these cosmic messengers requires sustained investment in detection and characterization capabilities that enable recognition and analysis of such visitors. The technologies that allowed identification of 3 IATLAS as an interstellar object, rather than just another faint comet, represent decades of scientific development and international coordination. These capabilities require ongoing support, technological advancement, and political commitment from institutions worldwide. The long intervals between spectacular discoveries or obvious threats can make continued investment seem less urgent. This would represent a profound miscalculation. We are finally developing observational and analytical tools needed to understand our place within galactic processes that have operated for billions of years. The coming decades could witness revolutionary advances in our comprehension of planetary formation, stellar evolution, and galactic chemical development, based on direct sampling of interstellar materials delivered naturally to our telescopes. In the quiet pre-dawn hours of December 2025, when 3 IATLAS first becomes visible again to telescopes worldwide, humanity will witness something unprecedented in our species' history. For the first time, we will observe in real time how an authentic piece of another star system responds to heating from our sun, how ancient chemistry from galactic deep time behaves when subjected to stellar radiation that originated in our local cosmic neighborhood. The observations may reveal whether billions of years of interstellar processing have fundamentally altered the object's composition, or whether pristine signatures from its formation environment remain preserved in subsurface layers now being exposed by solar heating. Each spectroscopic detection will provide direct evidence about stellar nucleosynthesis rates, planetary disk chemistry, and volatile inventories that existed during epochs we can study no other way. But perhaps the most profound revelation isn't what 3 IATLAS tells us about distant stellar systems or ancient galactic environments. Perhaps the deepest insight involves recognizing that we inhabit a universe far more dynamic and interconnected than our daily experience suggests. The cosmos continuously creates, destroys, and redistributes matter across scales that dwarf human comprehension, yet occasionally delivers samples of these processes directly to our scientific instruments. This recognition transforms our relationship with both the immediate terrestrial environment and the broader galactic community. We are not isolated observers of cosmic phenomena, but active participants in material exchange processes that connect stellar systems across vast regions of space and time. The same elements that comprise our bodies, our atmosphere, and our technological civilization have participated in these exchanges for longer than our planet has existed. Understanding this connectivity doesn't diminish human significance, but rather places our existence within a context of cosmic creativity that spans billions of years and countless stellar generations. We represent one outcome of processes that began when the universe was younger and will continue long after our sun expires. Yet our capacity to recognize, study, and appreciate these connections makes us conscious participants in galactic-scale evolution. As winter deepens and 3 IATLAS prepares for its December reappearance, this ancient traveler will continue its predetermined trajectory through our solar system and back into the interstellar medium. By March 2026, it will pass within 54 million kilometers of Jupiter, receiving one final gravitational nudge that will slightly alter its path before departing our cosmic neighborhood forever. The comet's exit velocity will carry it back into the vast spaces between stars, where it will resume the solitary journey that brought it to our attention. Future encounters with other stellar systems remain possible but unpredictable, dependent on gravitational influences and cosmic accidents that operate across timescales exceeding human civilization. Yet the information extracted during its brief passage through our observational capabilities will continue generating scientific insights for years or decades to come. Chemical compositions, isotopic ratios, and physical properties documented during these months will be compared with future interstellar visitors, gradually building a comprehensive database of galactic material exchange processes. More visitors will arrive. Current models suggest at least one detectable interstellar object should pass through our solar system every few years, though improved survey capabilities may reveal much higher frequencies. Each new arrival will carry unique signatures reflecting different stellar environments, formation conditions, and evolutionary histories. The accumulated knowledge from studying these cosmic messengers may eventually enable reconstruction of galactic chemical evolution, mapping how star formation, planetary development, and material redistribution have proceeded across different regions and epochs of our galaxy's history. We may discover that the ingredients for biological complexity are distributed far more widely than current theories suggest, or that planetary formation follows patterns we haven't yet recognized. Standing beneath clear skies in the months ahead, knowing that this ancient wanderer moves silently overhead, carrying messages from stellar environments that existed before our world began forming, we gain perspective on both the magnificent scale of cosmic processes and the remarkable circumstances that allow conscious beings to recognize and study them. 3. IATLAS will eventually fade from our telescopes and return to the darkness between stars. But the questions it raises about galactic connectivity, material exchange, and our place within these vast systems will continue shaping human understanding for generations to come. In a universe where matter constantly travels between worlds across distances and timescales that challenge imagination, every clear night offers opportunities to contemplate the cosmic community of which we are, and have always been, integral participants. The ancient wanderer's message is ultimately one of connection. We exist within a galaxy that has been exchanging the building blocks of worlds for longer than our solar system has existed. Tonight, as 3IATLAS continues its billion-year journey, we can look up and recognize ourselves as temporary custodians of elements that have traveled between the stars, participating in processes that connect us to every corner of our cosmic home. But there's something happening right now that most people aren't talking about. Something that reveals just how interconnected our cosmic neighborhood truly is. As 3IATLAS continues its ancient dance through our solar system, it's participating in what astronomers call gravitational choreography, a delicate ballet of forces that connects every object in our stellar family. Each planetary encounter subtly reshapes the comet's trajectory through mathematical precision that would make Newton weep with joy. When 3IATLAS passes within 97 million kilometers of Venus on November 3, 2025, the planet's gravitational field will imperceptibly adjust the visitor's path. The effect seems negligible, perhaps altering the comet's velocity by mere meters per second. Yet these tiny changes accumulate across astronomical distances to determine where this wanderer will travel for the next million years. Jupiter's influence proves far more dramatic. The gas giant's immense gravitational well, positioned strategically along 3/ATLAS's exit route, will provide one final cosmic handshake on March 16, 2026. This encounter, at 54 million kilometers, represents the solar system's farewell gesture. a gravitational assist that will add energy to the comet's hyperbolic trajectory and accelerate its return to interstellar space. What fascinates researchers isn't just the mechanical precision of these interactions, but their implications for understanding how matter moves through our scales. Every galaxy on geological time interstellar visitor that passes through our cosmic neighborhood experiences similar gravitational modifications, creating a complex web of trajectories that connect stellar systems across vast regions of space. Dr. Sarah Johnson from the Jet Propulsion Laboratory describes these processes with characteristic scientific precision. The gravitational signatures imparted by our solar system's architecture will remain embedded in 3I/ATLAS's trajectory long after it departs our observational range. Future civilizations that encounter this object millions of years hence could potentially decode these signatures to reconstruct the mass distribution and planetary configuration of our stellar system. This realization transforms our perspective on cosmic archaeology. We're not merely passive observers studying ancient visitors from other worlds. We're active participants in a galactic information network, encoding details about our solar system's properties into every object that passes through our gravitational sphere of influence. While gravitational forces reshape 3I/ATLAS's future trajectory, solar radiation continues unlocking molecular memories preserved since the comet's formation billions of years ago. Each day brings the ancient wanderer closer to peak solar heating, driving increasingly vigorous sublimation of volatiles that have remained frozen throughout its interstellar journey. The progressive activation of different chemical species creates what researchers describe as molecular archaeology in real time. Carbon dioxide, with its relatively low sublimation temperature, began outgassing when the comet was still beyond Mars's orbit. As 3I/ATLAS approaches perihelion, water ice activation will trigger secondary phases of chemical evolution with potentially different optical properties and spectroscopic signatures. Some researchers propose that this sequential volatile activation might expose subsurface layers containing pristine materials from the comet's original formation environment. If thermal processing proceeds gradually enough, telescopic observations could effectively excavate through billions of years of accumulated surface modifications to reach chemical signatures that predate our solar system's existence. The implications extend beyond individual molecular detections. Isotopic ratios preserved in the comet's ancient ice could provide direct measurements of stellar nuclear synthesis rates operating when our galaxy was younger and more chemically active. Heavy element abundances might reflect supernova enrichment patterns from epochs when massive star formation exceeded current rates by significant factors. Dr. Elena Rodriguez, leading isotopic analysis at the European Southern Observatory, emphasizes the unprecedented nature of these opportunities. Most astronomical observations provide information about distant objects at the time their light was emitted, creating inevitable delays between cosmic events and human detection. With 3I/ATLAS, we're studying authentic material samples in real time as they respond to heating from our local star. This temporal immediacy allows researchers to observe chemical processes that would remain invisible in distant objects. Sublimation rates, volatile ratios, and molecular formation mechanisms can be measured with precision impossible for extrasolar observations, providing ground truth data for understanding similar processes operating around other stars throughout the galaxy. Yet perhaps the most intriguing aspect of 3I/ATLAS isn't what it reveals about ancient galactic chemistry, but what its very existence tells us about the resilience of matter under extreme conditions. This object has survived a journey that spans geological timescales while maintaining sufficient structural integrity to produce vigorous cometary activity when heated by our Sun. The survival paradox challenges conventional understanding of how small bodies evolve during extended exposure to the interstellar medium. Cosmic ray bombardment should have gradually altered surface chemistry through nuclear reactions. micrometeorite impacts should have eroded exposed materials. Thermal cycling during encounters with stellar radiation fields should have created internal stresses leading to mechanical fragmentation. Instead, 3IATLAS arrives, displaying robust outgassing capabilities and coherent structural properties that suggest remarkable preservation of its primordial characteristics. Some researchers speculate that the object's large size relative to previous interstellar visitors may have provided sufficient thermal mass to maintain internal stability during its billion-year odyssey. Alternative theories propose that interstellar objects undergo continuous self-repair through sublimation and redeposition processes that gradually heal radiation damage and impact scars. This concept suggests that cometary nuclei function as dynamic systems capable of maintaining structural integrity across cosmic timescales through ongoing material exchange with their immediate environment. The survival mechanisms operating in interstellar space remain poorly understood, partly because 3IATLAS represents only our third opportunity to study such objects directly. Each new visitor provides additional data points for understanding how matter behaves during extended journeys between stellar systems, gradually building theoretical frameworks that could predict the properties and populations of interstellar debris throughout our galactic neighborhood. While 3IATLAS captured scientific attention through its unusual properties and ancient origins, its discovery also highlights a quiet revolution occurring in our ability to monitor cosmic traffic passing through our solar system. The Atlas Survey telescope that first detected this interstellar wanderer represents just one component of an expanding global network designed to catalogue objects moving through near-Earth space. The Vera Rubin Observatory, which achieved first light during 2025, will eventually provide unprecedented capability for discovering and tracking small bodies throughout the solar system. Its enormous mirror and wide-field camera can rescan the entire accessible sky every few nights with sensitivity that far exceeds previous survey systems. Early operations have already demonstrated the facility's potential by detecting thousands of new asteroid candidates during just 10 hours of observation. Enhanced survey capabilities raise profound questions about the true frequency of interstellar visitors passing through our cosmic neighborhood. Current statistical models, based on limited observational data from just 3 confirmed interstellar objects, suggest such visitors should remain relatively rare. But if these estimates prove conservative, improved detection systems might reveal that our solar system receives far more interstellar traffic than previously recognized. Dr. Michael Chen, directing the survey operations at Rubin Observatory, describes the potential for discovery as genuinely transformative. If dozens or hundreds of interstellar objects pass through our solar system annually, most remaining undetected due to small size or low activity levels, then enhanced survey coverage could revolutionize our understanding of galactic material exchange processes. Such revelations would fundamentally alter our conception of planetary system isolation. Rather than viewing Earth and its companions as products of purely local stellar formation, we would recognize ourselves as participants in galaxy-wide ecosystems, where matter constantly flows between stellar systems across vast distances and timescales. The comprehensive study of 3IATLAS has been enabled by a remarkable convergence of technological capabilities that didn't exist during previous interstellar visitor encounters. Space-based infrared telescopes, advanced spectroscopic instruments, and coordinated international observation networks provide unprecedented capability for characterizing authentic samples from other stellar systems. NASA's James Webb Space Telescope, with its extraordinary sensitivity to infrared radiation, can detect molecular emissions from cometary comas with precision impossible just decades ago. The facility's ability to analyze light across multiple wavelength bands simultaneously allows researchers to identify chemical species and measure abundance ratios that reveal formation conditions billions of years in the past. Complementary observations from the Hubble Space Telescope provide high-resolution imaging that documents structural changes in real time as 3IATLAS responds to increasing solar heating. The visual documentation creates both scientific records and artistic representations of this ancient visitor's transformation during its passage through our solar system. Ground-based facilities contribute essential spectroscopic monitoring that tracks chemical evolution on timescales ranging from hours to months. The Very Large Telescope in Chile has provided continuous observations, documenting the steady increase in volatile emissions as the comet approaches perihelion, generating quantitative data about outgassing rates and molecular formation processes. This technological convergence extends beyond individual instruments to include sophisticated coordination mechanisms that enable simultaneous observations from multiple platforms. International cooperation protocols developed for studying 3 IATLAS will prove directly applicable to future interstellar visitors and potentially hazardous asteroids requiring rapid characterization. As we prepare for 3 I/ATLAS to complete its solar system passage and return to the interstellar medium, the object's brief visit raises profound questions about humanity's relationship with cosmic processes operating on galactic scales. This ancient wanderer has provided our first detailed glimpse of authentic material from stellar environments that existed before our solar system formed. The philosophical implications extend beyond scientific discovery to challenge fundamental assumptions about isolation and connectivity in cosmic evolution. We are not separate from galactic processes, but integral participants in material exchange systems that have operated for longer than our planet has existed. The elements comprising our bodies, our atmosphere, and our technological civilization have participated in these exchanges across geological time. Recognition of this connectivity transforms environmental stewardship from local concern to cosmic responsibility. We serve as temporary custodians of materials that originated in other stellar systems and will eventually continue their galactic journey. Our choices about planetary resource management and technological development occur within contexts that span far greater scales of space and time than typically acknowledged. Dr. Lisa Patel, reflecting on the broader implications at the Institute for Advanced Study, emphasizes that 3 IATLAS functions as more than scientific curiosity. The object represents direct physical evidence of processes that connect our local cosmic environment to the broader galactic community across vast distances and timescales that challenge human comprehension. This perspective doesn't diminish human significance, but rather places our existence within frameworks of cosmic creativity that began when the universe was younger and will continue long after our sun expires. Our capacity to recognize, study, and appreciate these connections makes us conscious participants in galactic evolution rather than isolated observers of distant phenomena. The ancient wanderer's message ultimately concerns connection rather than separation. We exist within a galaxy that has been exchanging the building blocks of worlds for longer than our solar system has existed, participating in processes that link us to stellar nurseries throughout our cosmic neighborhood and beyond. In the quiet hours before dawn, when 3 IATLAS first becomes visible again to telescopes worldwide in December 2025, humanity will witness something unprecedented in our species' history. For the first time, we will observe in real time how an authentic piece of another star system responds to heating from our sun, how ancient chemistry from galactic deep time behaves when subjected to stellar radiation that originated in our local cosmic neighborhood. The December observations may reveal whether billions of years of interstellar processing have fundamentally altered the object's composition, or whether pristine signatures from its formation environment remain preserved in subsurface layers now being exposed by solar heating. Each spectroscopic detection will provide direct evidence about stellar nucleosynthesis rates, planetary disk chemistry, and volatile inventories that existed during epochs we can study no other way. Yet, as 3 IATLAS prepares for its final departure from our observational range, the most profound revelation may not involve what this visitor tells us about distant stellar systems or ancient galactic environments. Perhaps the deepest insight concerns recognizing that we inhabit a universe far more dynamic and interconnected than our daily experience suggests. The cosmos continuously creates, destroys, and redistributes matter across scales that dwarf human comprehension, yet occasionally delivers samples of these processes directly to our scientific instruments. This recognition transforms our relationship with both the immediate terrestrial environment and the broader galactic community. Standing beneath clear skies in the months ahead, knowing that this ancient wanderer moves silently overhead, carrying messages from stellar environments that existed before our world began forming, we gain perspective on both the magnificent scale of cosmic processes and the remarkable circumstances that allow conscious beings to recognize and study them. 3IATLAS will eventually fade from our telescopes and return to the darkness between stars, resuming the solitary journey that brought it to our attention. Future encounters with other stellar systems remain possible but unpredictable, dependent on gravitational influences and cosmic accidents that operate across timescales exceeding human civilization. But the information extracted during its brief passage through our observational capabilities will continue generating scientific insights for years or decades to come. Chemical compositions, isotopic ratios, and physical properties documented during these months will be compared with future interstellar visitors, gradually building comprehensive understanding of galactic material exchange processes. More visitors will arrive. Enhanced survey capabilities may reveal that our solar system receives far more transforming cosmic archaeology from speculative science interstellar traffic than current models suggest, into systematic survey discipline galactic environments, to night formation across different capable of mapping chemical and physical properties of planetary. As 3IATLAS, our cosmic continues its billion-year journey through neighborhood, we can look up and recognize that have traveled between the stars. Ourselves as temporary custodians of elements, we participate in processes that connect us to every corner of our galactic home, conscious witnesses to the eternal circulation of matter that links worlds across vast expanses of space and time. The ancient wanderer carries within its frozen nucleus not just chemical signatures from another stellar system, but proof that we live in a universe where nothing remains truly isolated. Every atom in our bodies has participated in cosmic processes spanning billions of years. Every breath we take contains elements forged before our sun ignited, injured in stellar furnaces that expire this recognition. 3IATLAS offers its greatest gift: perspective on our place within galactic evolution that has proceeded for longer than our solar system has existed and will continue long after our star joins the cosmic recycling that connects all matter across the vast community of worlds we call home. But there's something else happening here that challenges our understanding of cosmic mechanics in ways most people haven't considered. As 3IATLAS continues its predetermined path through our solar system, subtle influences are at work that extend far beyond simple gravitational interactions. The comet's passage creates what researchers describe as dynamic resonance patterns throughout our local space environment. Every object in our solar system exists within an intricate web of gravitational relationships. And when something as massive and fast-moving as 3IATLAS threads through this network, it generates ripple effects that propagate across astronomical distances. Dr. Rebecca Martinez from the European Space Operations Centre has been monitoring these cascading influences with unprecedented precision. Her team's calculations reveal that 3IATLAS imparts measurable perturbations to dozens of smaller objects in the outer solar system, creating trajectory modifications that will accumulate over thousands of years to produce significant orbital changes. These aren't dramatic alterations that threaten planetary stability. Rather, They represent subtle adjustments to the cosmic clockwork that governs long-term orbital evolution throughout our stellar neighborhood. Some asteroids will arrive at different positions decades hence because of gravitational nudges they're receiving right now from our interstellar visitor. The implications extend beyond mechanical orbital adjustments. As 3IATLAS moves through the solar wind, its extensive coma and tail create electromagnetic disturbances that interact with charged particle populations throughout the heliosphere. These interactions generate what plasma physicists describe as information cascades, where local modifications to magnetic field configurations propagate outward at the speed of light. The electromagnetic signature of 3IATLAS tells a story that reaches far beyond its immediate vicinity. As ancient volatiles sublime from the comet's nucleus, they create ionized gas clouds that become electromagnetically coupled to solar wind magnetic field lines. This coupling generates radio emissions detectable by sensitive instruments across multiple frequency ranges. Dr. James Liu at the Very Large Array in New Mexico has been monitoring these emissions with fascination. The comet's radio signature contains modulations that appear to correlate with its rotational period, suggesting that different regions of the nucleus are contributing distinct chemical components to the expanding coma. But more intriguingly, some researchers have identified periodic variations in the emissions that don't match the comet's rotation rate. These mysterious modulations might reflect internal structural changes as thermal gradients penetrate deeper into the nucleus, exposing subsurface materials with different electromagnetic properties. The radio observations provide complementary information to optical spectroscopy, revealing processes that remain invisible to traditional telescopic observations. Molecular ions created through photoionization and electron impact processes emit characteristic radio signatures that can be decoded to understand the comet's internal composition and outgassing dynamics. Some researchers propose that these electromagnetic interactions might preserve information about the interstellar medium through which 3I/ATLAS traveled during its billion-year journey. Magnetic field orientations embedded in the comet's plasma environment could theoretically retain signatures of stellar wind encounters or interstellar magnetic field configurations experienced during its odyssey between stars. As we delve deeper into the scientific implications of 3IATLAS, a fascinating paradox emerges regarding the nature of time and cosmic evolution. This ancient wanderer simultaneously represents the distant past and immediate present in ways that challenge conventional thinking about astronomical observation. Most cosmic phenomena we study occurred millions or billions of years ago, with light travel time creating inevitable delays between distant events and human detection. When we observe distant galaxies, we see them as they existed when the universe was younger. When we analyze stellar spectra, we examine light emitted years or decades ago, depending on the star's distance. 3IATLAS breaks this temporal separation. We're studying authentic material from stellar environments that existed billions of years ago, yet observing these materials in real time as they respond to heating from our contemporary sun. The chemical processes unfolding in the comet's coma represent direct interaction between ancient galactic chemistry and modern stellar radiation. Dr. Patricia Chen at the Institute for Theoretical Astrophysics describes this as observational time travel without the usual constraints of light-speed communication. The molecular emissions we detect today carry information about formation conditions that preceded our solar system's existence, yet we observe these signatures without temporal delay. This temporal immediacy allows researchers to study how ancient materials behave under controlled conditions, providing ground truth data for understanding similar processes operating around other stars throughout cosmic history. The insights gained from 3I/ATLAS could refine theoretical models of planetary formation, stellar evolution, and galactic chemical enrichment across vast timescales. The passage of 3IATLAS through our solar system reveals something profound about the nature of information transfer in cosmic evolution. This object functions as more than a messenger, carrying chemical signatures from distant stellar environments. It represents an active participant in a galactic information network that has operated for longer than our planet has existed. Every gravitational interaction during the comet's solar system passage encodes details about our local stellar architecture into its future trajectory. Civilizations that might encounter 3 IATLAS millions of years hence could potentially decode these gravitational signatures to reconstruct the mass distribution and orbital characteristics of our planetary system. Conversely, the comet's current properties preserve information about every stellar encounter it experienced during its interstellar journey. Close approaches to other stars would have modified its orbit, composition, and internal structure, inevitably reconstruct aspects. Careful analysis of these modifications could theoretically be detectable in various ways. Of 3 IATLAS's billion-year voyage through the galaxy. Some researchers speculate that this information encoding and transfer represents a fundamental aspect of galactic evolution. Every object ejected from planetary systems carries encoded data about its origins. Every gravitational encounter modifies and adds new information. Over geological timescales, this process creates a vast distributed database of stellar system properties accessible through careful analysis of interstellar debris. The concept transforms our understanding of cosmic archaeology from passive observation of ancient light to active participation in ongoing information exchange processes. We're not merely studying 3 IATLAS as an isolated curiosity, but engaging with a galactic communication network that connects stellar systems across vast regions of space and time. The scientific revelations emerging from 3 IATLAS studies are generating cascade effects throughout multiple fields of astronomical research. Chemical compositions that seemed impossible for comet formation are forcing revisions to theoretical models of planetary system evolution. Survival mechanisms that preserved structural integrity across billion-year timescales are influencing understanding of matter behavior under extreme conditions. Dr. Maria Santos at the Planetary Science Institute emphasizes that every unusual characteristic discovered in 3 IATLAS raises fundamental questions about assumed universality in cosmic processes. If this condition's dramatically different from those interstellar visitor formed under that created solar system objects, then planetary formation might follow diverse pathways we haven't yet recognized. The implications extend to astrobiology and the search for life beyond Earth. If stellar systems throughout the galaxy produce planetary debris with widely varying chemical signatures, then the ingredients essential for biological processes might be distributed in patterns that differ significantly from current theoretical predictions. Enhanced survey capabilities that will detect future interstellar visitors are already being redesigned based on lessons learned from studying 3 IATLAS. The object's faint magnitude and subtle spectroscopic features required pushing observational technologies to their limits, revealing capabilities and limitations that will guide development of next-generation detection systems. International cooperation protocols established for coordinating 3 IATLAS observations are being formalized as templates for studying future cosmic visitors. The successful integration of space-based and ground-based observational platforms demonstrates possibilities for comprehensive characterization that will prove essential when more exotic objects arrive. As 3 IATLAS approaches its final weeks of visibility before disappearing behind solar glare, its presence in our cosmic neighborhood has catalyzed something approaching philosophical awakening regarding humanity's relationship with galactic processes. This ancient wanderer has provided tangible evidence of connections that span scales difficult for human consciousness to fully comprehend. The realization that matter comprising our bodies has participated in cosmic recycling for longer than our solar system has existed transforms abstract concepts of cosmic unity into concrete scientific reality. We are not separate from galactic evolution, but integral components of processes that have operated across geological time to create and distribute the elements essential for complex chemistry and biological development. This recognition carries implications that extend beyond academic astronomy to influence perspectives on environmental stewardship, international cooperation, and technological development. Our choices about planetary resource management occur within contexts that connect us to stellar communities throughout our galactic neighborhood and beyond. Dr. Elena Rodriguez, reflecting on the broader significance at the European Southern Observatory, suggests that 3I/ATLAS functions as a catalyst for expanded cosmic consciousness. The object provides direct physical evidence of processes that link our local environment to galactic evolution across time scales that challenge conventional thinking about isolation and connectivity. Yet this expanded awareness doesn't diminish human significance, but rather places our existence within frameworks of creativity and complexity that began when the universe was younger and will continue long after our sun joins the cosmic recycling that connects all matter throughout space and time. Now, as autumn deepens and 3I/ATLAS continues its ancient trajectory towards solar conjunction, we approach what may prove to be the most scientifically valuable period in the history of interstellar visitor observation. The comet's temporary disappearance behind solar glare, beginning in late September, will end with dramatic re-emergence in early December under optimal viewing conditions. Dr. Michelle Bannister's trajectory calculations indicate that 3I/ATLAS will first become visible again to ground-based telescopes on December 3rd, position dawn skied in the pre, where atmospheric interference reaches minimum levels. The object's apparent magnitude should have increased significantly due to enhanced solar heating during perihelion passage, potentially making detailed spectroscopic analysis easier than during its initial discovery phase. Professional observatories worldwide have already begun preparing coordinated observation campaigns designed to extract maximum scientific value from the December viewing window. The European Southern Observatory is dedicating substantial telescope time to high-resolution spectroscopy, while NASA's space-based assets maintain continuous monitoring capabilities that complement ground-based efforts. The December observations may resolve fundamental questions about 3I/ATLAS's survival and structural integrity. Did the intense solar heating at perihelion fragment the ancient nucleus into multiple components? Or did billions of years of interstellar conditioning prepare this wanderer to survive thermal stresses that destroy less experienced comets? Amateur astronomers with sophisticated equipment are also preparing for December observations. While 3I/ATLAS will remain too faint for casual viewing, experienced astrophotographers using CCD cameras and precision tracking systems should be able to document morphological changes and contribute valuable data to professional research efforts. In the quiet pre-dawn hours of December 2025, when telescopes worldwide first capture 3I/ATLAS emerging from behind our star's overwhelming brightness, humanity will witness something unprecedented in our species' history. We will observe in real time how authentic material from another stellar system responds to heating from our sun, how chemistry preserved for billions of years behaves when subjected to contemporary stellar radiation. The observations may reveal whether the comet's passage through perihelion fundamentally altered its ancient composition, or whether pristine signatures from its formation environment remain accessible in newly exposed subsurface materials. Each spectroscopic detection will provide direct evidence about stellar nucleosynthesis, planetary chemistry, and volatile evolution during epochs we can study through no other means. Yet as 3I/ATLAS prepares to complete its solar system passage and return to interstellar space, perhaps the most profound revelation involves recognizing that we inhabit a universe far more dynamic and interconnected than than our terrestrial experience typically suggests. The cosmos continuously creates, destroys, and redistributes matter across scales that dwarf human comprehension, occasionally delivering samples of these processes directly to our scientific instruments. Standing beneath clear skies in the months ahead, knowing that this ancient messenger moves silently overhead, carrying chemical signatures from stellar environments that existed before our world began forming, we gain perspective on both the magnificent scale of cosmic creativity and the extraordinary circumstances that allow conscious beings to recognize and appreciate these connections. 3. IATLAS will eventually fade from our telescopes and resume the journey that brought it to our attention. Future encounters with other stellar systems remain possible but unpredictable, dependent on gravitational influences and cosmic circumstances that operate across timescales exceeding human civilization. The information extracted during its brief passage through our observational range will continue generating insights for decades to come, building comprehensive understanding of galactic material exchange that connects stellar systems across vast expanses of space and time. More visitors will arrive, each carrying unique signatures that illuminate different aspects of cosmic evolution and planetary formation throughout our galactic community. Tonight, as 3IATLAS continues its billion-year odyssey through the darkness between worlds, we can look upward and recognize ourselves as temporary custodians of elements that have traveled between stars, conscious participants in processes that link us to every corner of our cosmic home. The ancient wanderer's greatest gift may ultimately be this recognition. We exist within a galaxy that has been exchanging the building blocks of worlds for longer than our solar system has existed, part of an eternal circulation of matter that connects all worlds across the vast community we call the universe. As we reach the final phase of our cosmic investigation, something extraordinary emerges from the data streams flowing back from our most sophisticated instruments. While 3IATLAS prepares for its hidden solar encounter, the chemical signatures detected during these crucial weeks reveal what researchers describe as a molecular memory vault, preserving information about galactic conditions that existed before our solar system formed. The progressive activation of different volatile compounds creates what some scientists characterize as temporal archaeology unfolding in real time. Carbon dioxide, with its relatively low sublimation temperature, began its release when the ancient wanderer remained beyond Mars's orbital distance. As solar heating intensifies, water ice activation triggers secondary phases of chemical evolution, each carrying distinct spectroscopic fingerprints that illuminate different epochs of cosmic history. Dr. Elena Rodriguez at the European Southern Observatory suggests these sequential volatile releases might effectively excavate through billions of years of accumulated surface modifications. If thermal processing proceeds gradually enough, telescopic observations could potentially reach chemical signatures that predate our solar system's existence, offering unprecedented access to primordial galactic chemistry. The isotopic ratios preserved within these ancient ices provide direct measurements of stellar nucleosynthesis operating when our galaxy was younger and more chemically active. Heavy element abundances reflect supernova enrichment patterns from epochs when massive star formation significantly exceeded current rates, creating a natural laboratory for understanding cosmic chemical evolution across geological timescales. What makes these observations particularly remarkable is their temporal immediacy. Most astronomical studies examine distant objects as they existed when their light began its journey toward Earth, creating inevitable delays between cosmic events and human detection. With 3IATLAS, researchers analyze authentic material samples responding to contemporary stellar heating, eliminating the usual constraints of light-speed communication across cosmic distances. This unique circumstance allows scientists to observe chemical processes that would remain invisible in distant stellar systems. sublimation rates, molecular formation mechanisms, and volatile interactions can be measured with precision impossible for extrasolar observations, providing essential calibration data for understanding similar processes throughout galactic history. But perhaps the most thought-provoking aspect of 3IATLAS involves recognizing its role within what some researchers describe as a galactic information network that has operated for longer than our planet has existed. Every gravitational interaction during the comet's solar system passage encodes specific details about our local stellar architecture into its future trajectory. Dr. Rebecca Martinez from the European Space Operations Centre has calculated that civilizations encountering 3IATLAS millions of years hence could potentially decode these gravitational signatures to reconstruct the mass distribution and orbital characteristics of our planetary system. The mathematical precision of celestial mechanics ensures that each planetary encounter leaves permanent modifications to the visitor's hyperbolic trajectory. Conversely, the comet's current properties preserve encoded information about every stellar encounter experienced during its interstellar odyssey. Close approaches to other stars would have modified its orbit, composition, and internal structure in mathematically predictable ways. Careful analysis of these modifications could theoretically reconstruct aspects of the object's billion-year voyage through different galactic neighborhoods. Some theoretical astrophysicists propose that this information encoding and transfer represents a fundamental characteristic of galactic evolution. Every object ejected from planetary systems carries embedded data about its origins. Every gravitational encounter modifies and supplements this information. Over geological time scales, this process creates what could be characterized as a vast, distributed database of stellar system properties, accessible through detailed analysis of interstellar debris. This concept transforms our understanding of cosmic archaeology from passive observation of ancient light to active participation in ongoing information exchange processes, connecting stellar communities across vast regions of space and time. We engage with 3IATLAS, not merely as an isolated curiosity, but as a participant in galactic communication networks that have facilitated material and information transfer throughout cosmic history. The implications extend beyond theoretical frameworks to influence practical approaches toward understanding our cosmic environment. If interstellar objects function as carriers of encoded galactic information, then enhanced detection and characterization capabilities become essential tools for decoding the history and structure of stellar populations throughout our galactic neighborhood. As autumn transitions toward winter and 3IATLAS continues its predetermined path towards solar conjunction, we approach what many researchers consider the most scientifically valuable period in the history of interstellar visitor observation. The comet's temporary disappearance behind solar brilliance will conclude with dramatic re-emergence under optimal viewing conditions that may never again align so favorably for human astronomy. Dr. Michelle Bannister's precise trajectory calculations indicate that 3IATLAS will first become visible to ground-based telescopes on December 3rd, positioned in pre-dawn skies, where atmospheric interference reaches minimum levels. The object's apparent brightness should increase significantly due to enhanced solar heating during perihelion passage, potentially facilitating detailed spectroscopic analysis that surpasses capabilities available during its initial discovery phase. Professional observatories worldwide have dedicated substantial resources to coordinated observation campaigns designed to extract maximum scientific value from this crucial viewing window. The European Southern Observatory allocated significant telescope time for high-resolution spectroscopy, while space-based assets maintain continuous monitoring capabilities that complement ground-based efforts through multiple wavelength ranges. These December observations may resolve fundamental questions about structural survival and chemical evolution that have remained unanswered since the comet's discovery. Did intense solar heating at perihelion fragment the ancient nucleus into multiple components? Or did billions of years of interstellar conditioning prepare this wanderer to survive thermal stresses that typically destroy less experienced comets. Amateur astronomers equipped with sophisticated instrumentation are also preparing for December observations, while 3I/ATLAS will remain too faint for casual viewing. Experienced astrophotographers using precision tracking systems and sensitive detectors should contribute valuable morphological documentation that supplements professional research efforts. The stakes for these observations extend beyond academic curiosity to encompass our fundamental understanding of how matter behaves during extended journeys between stellar systems. Every spectroscopic detection during the December window provides direct evidence about galactic chemical processes operating across timescales that challenge human comprehension. The revelations emerging from 3IATLAS studies are generating what some researchers describe as cascade effects throughout multiple disciplines of astronomical investigation. Chemical compositions that seemed impossible according to conventional comet formation models are necessitating comprehensive revisions to theoretical frameworks governing planetary system evolution. Dr. Maria Santos at the Planetary Science Institute emphasizes that every unusual characteristic discovered in this interstellar visitor raises fundamental questions about assumed universality in cosmic processes. If 3IATLAS formed under conditions dramatically different from those that created objects within our solar system, then planetary formation throughout the galaxy might follow diverse pathways that remain largely unrecognized by current theoretical models. The implications extend significantly into astrobiology and the search for life beyond Earth. If stellar systems throughout the galaxy produce planetary debris with widely varying chemical signatures, then essential ingredients for biological processes might be distributed according to patterns that differ substantially from current theoretical predictions about habitability and organic chemistry distribution. Enhanced survey capabilities designed to detect future interstellar visitors are already being modified based on lessons learned from studying 3IATLAS. The object's relatively faint magnitude and subtle spectroscopic features required pushing observational technologies toward their operational limits, revealing both capabilities and constraints that will guide development of next-generation detection systems. International cooperation protocols established for coordinating 3IATLAS observations are being formalized as templates for studying future cosmic visitors. The successful integration of space-based and ground-based observational platforms demonstrates comprehensive characterization possibilities that will prove essential when more scientifically challenging objects arrive within our detection range. The technological convergence that enabled detailed study of this ancient wanderer represents a remarkable achievement in human scientific capability. Space-based infrared telescopes, advanced spectroscopic instruments, and coordinated international observation networks provide unprecedented ability to characterize authentic samples from stellar systems that existed billions of years before our Sun began nuclear fusion. As 3IATLAS approaches its final weeks of visibility before disappearing behind solar radiance, its presence within our cosmic neighborhood has catalyzed something approaching philosophical transformation regarding humanity's relationship with galactic-scale processes. This ancient messenger has provided tangible evidence of connections that span temporal and spatial scales difficult for human consciousness to fully comprehend. Tonight, as we conclude our journey through the cosmic mysteries surrounding 3IATLAS, we're left with something far more profound than mere scientific data. This ancient wanderer has revealed that we exist within a universe where matter continuously circulates between worlds across distances and timescales that dwarf imagination. Every element in our bodies has participated in this eternal exchange, connecting us to stellar nurseries throughout our galactic neighborhood and beyond. As 3IATLAS fades from our telescopes and resumes its billion-year odyssey through the darkness between stars, it leaves us with the recognition that we are temporary custodians of elements that have traveled between worlds, conscious participants in processes that link every corner of our cosmic home. In this vast community we call the universe, nothing remains truly isolated, and every clear night offers opportunities to contemplate our place within the magnificent circulation of matter that connects all worlds across space and time. The realization that matter comprising our bodies has participated in cosmic recycling for longer than our solar system has existed transforms abstract concepts of cosmic unity into concrete scientific reality. We are not separate from galactic evolution, but integral components of processes that have operated across geological time to create and distribute the elements essential for complex chemistry and biological development. This recognition carries implications that extend beyond academic astronomy to influence perspectives on environmental stewardship, international cooperation, and technological development. Our choices about planetary resource management occur within contexts that connect us to stellar communities throughout our galactic neighborhood and beyond. We serve as temporary custodians of materials that originated in other stellar systems and will eventually continue their galactic journey. As we stand beneath clear skies in the months ahead, knowing that this ancient messenger moves silently overhead, carrying chemical signatures from stellar environments that existed before our world began forming, we gain perspective on both the magnificent scale of cosmic creativity and the extraordinary circumstances that allow conscious beings to recognize and appreciate these connections. The enhanced survey capabilities that will detect future interstellar visitors could reveal that our solar system receives far more cosmic traffic than previously recognized, transforming our understanding from isolated planetary system to active participant in galaxy-wide material exchange. 3I ATLAS will eventually fade from our telescopes and resume the journey that brought it to our attention. But the questions it raises about galactic connectivity and our place within these vast systems will continue shaping human understanding for generations to come. More visitors will arrive, each carrying unique signatures that illuminate different aspects of cosmic evolution and planetary formation throughout our galactic community. The ancient wanderer's greatest gift may ultimately be this recognition. We exist within a galaxy that has been exchanging the building blocks of worlds for longer than our solar system has existed, part of an eternal circulation of matter that connects all worlds across the vast community we call the universe.